Okay, everyone, so last video we just did a very quick graphical example to try to illustrate how OLS is working by minimizing the sum of squared errors in order to obtain the line that best fits our data. So now we want to move into some of the five major assumptions that are necessary in order to obtain estimates of our parameters beta that are both unbiased and efficient. So OLS will be considered blue, the best linear unbiased estimator under the following few assumptions. So the first assumption is, we've already discussed, we assume that the relationship between y and our x's is linear. The second assumption is that we assume we have a random sample of n observations following the actual population. And what this means is if we're trying to understand effects of some kind of policy on the labor market and we only sample women, female workers who are in the employed, and then we try to generalize the effects of labor market policy on their outcomes, such as employment or salary. We clearly don't have a random sample because we're missing men from the sample. Only women are in our sample. So maybe we could say that we have a random sample of women workers and our results are generalizable to the female population of workers. But in general, whatever our generalization of our data is, it has to be considered, our observations need to be randomly selected. That is, every observation in our data have equal opportunity of being observed. The third one is no perfect multicollinearity. That means that among our x variables, we don't have x's that are extremely highly related to one another. So imagine if you're looking at individuals with very high level of education. If we have those who have received a PhD versus those who have only taken PhD coursework as two different variables and enter them into a model of human capital model, we could expect that the correlation is quite high among this group of population, given that A is very small share of population that have PhD or that have gone through PhD coursework. So we would imagine that there would be no reason to include individuals who have PhD coursework and those who have PhD. You would just use maybe one of those variables in order to avoid high multicollinearity problem. And for those of you who aren't quite clear, just give a very brief example where we have two x's that are exactly perfectly collinear, that is, they're identical variables. And we can see that some of the problems that arises is there's no unique solution to the model. So we don't know how the different variables are operating, and you can take a look at the explanations here to explain why multicollinearity induces problems or biasness into our estimates. So the most important assumption probably is this zero conditional mean assumption. What this states is that our error term is going, on average, is going to have an expected value of 0 given our explanatory variables or our x's. So the way we show this is our expected value, or on average, our error term conditional on our observed x's is going to be 0. That is, whatever is unobserved information that's contained in our error term, that is what we can't actually observe, we are assuming that there is no relationship or no correlation between that unobservable component of our model and the observable component that's captured by our various x's. Okay, so there's no relationship between our unobservables and our observables. And this assumption is easily violated for 3 different reasons. The most common one is usually omitted variable bias, but you can also have a misspecified functional form. Perhaps the relationship between y and x is a nonlinear as opposed to a linear function. And then you can have measurement error in either your y or x's. So as an example of the most common case of this omitted variable bias, We can assume a very simple example. We have a kind of Mincerian wage model here where our wages, workers' wages are predicted as a function of their education only. And all the other information on workers is going to be captured in our error term. That is, we don't actually observe it in our model. And we'll get an estimate for our beta 1 that will show us how strongly related education is to wage. The problem is that with this simple regression model, we're assuming that all of the information captured in this error term that we don't observe is not correlated to our education variable. Okay, there's no relationship. This is a very difficult assumption to make. For instance, we know that labor market experience is going to be related to those who have, related to education. For instance, people who don't have any college education will likely have more labor market experience, at least in the first few years. But obviously, in 10 or 15 years later, we would expect that education to have a much stronger effect on wages, holding constant experience. But in the beginning, it might look like the experience that people have in the first few years, while some workers are getting educated, they have fewer years of experience. There's going to be some trade-off or some relationship between the educational attainment of a worker and their work experience. So they're clearly related to each other. So if we only estimate this model, this parameter beta 1 would likely not be accurate. It wouldn't be efficient and it would be biased. So we would need to have all of the information contained here related to our education outcome needs to be properly specified in our model. Okay, so that's the probably the most important condition and most easily violated. Another assumption for OLS to be efficient and unbiased is this homoscedasticity assumption, where we assume that the error term has a constant variance sigma squared, conditioned on the observable components in the model. So we can take a very simple example, look at a multiple regression model using LM command and R, drawing in the diamonds data sets that's captured in the ggplot library. We have a few different variables here: the 4 C's, the carat, size of the diamond, the cut, the clarity, and the color, and how these 4 variables influence price. So we just run a very simple regression, and we're interested in looking at the diagnostics. So if we use the plot function of our model diamonds.lm, which we've assigned all the information here, if we run the plot command and select a couple of the plots, there's 4 plots total, we just select the first 2, what we'll see is a plot of the residuals of our model mapped against the fitted values for our y. And what we see as our fitted values increase in size, we see a very strong non-linear relationship between the residuals and the fitted. And we can see in the second plot this normal QQ plot, which is showing how whether or not our residuals follow a normal distribution. We can see that if there's a normal distribution, most of the circles should fall on this line here. But we can see there's large departures, especially at the lower and higher end of the quantiles, that are departing from a normal distribution. So this violation of homoscedasticity is a problem. So oftentimes a kind of an applied approach is to transform, take a logarithm of our variables, or some of our variables, the dependent variable or some of our independent variables. And if we rerun the log-log model and redo the plot, we can see that taking the log transformation allows our residuals to perform better. There's not much nonlinearity problem in the plot, and the residual looks much more normally distributed. Okay, so this is an example of the 5 major assumptions that we often assume when we run our OLS regression using the LM function in R, although it's very rare in practice for researchers, data scientists to show that these assumptions all hold, but it's good for background to know under what conditions do we expect OLS to give us our best estimate for our parameters to show us how strongly related our observed variables are to our outcome of interest. Okay, so in the next video, we'll take a look at how we can actually compute the OLS by hand and not rely on our LM function.